everyone, and welcome back. Today we're going to go ahead and talk about linear momentum and collisions. And of course, one may think, why do we care about this? Well, one very important thing is obviously how to play pool. I'm not one to necessarily be good at pool, but I understand the physics behind it. And in theory, I should be able to shoot one ball into the next ball and it should go into that corner pocket, but I can't seem to get that whole hitting that first ball correctly in the right direction. But that's one thing that we can actually use this, if you may have one of these at home, but I definitely don't, never have. But, when places start opening back up, you can go play pool, play billiards, and try to put this stuff to the test, okay? So that's the idea. I can hit ball A into ball, I don't know, this doesn't say which ball it is, we're going to call it ball B, and I can shoot it in such a way that it'll make that ball go in one direction and your initial ball in another direction. Okay, so that's really, a baseline of what we're going to talk about. Okay, that's a very simplistic form. So let's go ahead and first talk about linear momentum. Okay, so momentum is another way that we can characterize the quantity of a motion. So just like kinetic energy, we were able to talk about the motion of some object. We can describe its energy in motion. Okay, so now we're able to do that in another way, and momentum is defined as the product between an object's mass and its velocity. Okay, so notice one thing, you can even see by the soccer player, if he's kicking that ball in this direction, we have some velocity in this direction. Okay, we also have the momentum in that same direction. Okay, so you want to notice first that momentum and velocity will have the same direction. Okay, so if my momentum is in a negative x direction, then so will my velocity. Okay, and also notice these are both vectors. Okay, so they're both vector quantities. That's one thing also to note. Okay. So let's go ahead and talk about something else involved with momentum, and that's called impulse, okay? Impulse is really the change in momentum of some object, and that is proportional to the length of time during which some force is applied. So if we have that soccer ball and it's being kicked for some time t naught, okay, so it's got some force being applied for some time t naught, it'll have some impulse delta p. Okay, so this is impulse. Okay, and so we describe impulse as the product of a force and a time interval. Okay, let's go ahead and let f of t be a force applied to an object, just like these, over some differential time interval dt. Okay, so our resulting impulse would be defined as so. Okay. Now, one thing to note, if we kind of look at this formula, try to kind of play with what if I do this to the momentum or so forth. If I have twice the amount of momentum, that means I must have twice the amount of time or twice the amount of force. Okay. Or if I have twice the amount of time, then I'll have twice the amount of momentum. Okay, so kind of think of it as they are like linearly related. Okay, so this is a bit much. We don't have to go really into detail of this. This is what your textbook has. I'm going to try to pull back a little bit on how much detail I give you. There is quite a bit in this chapter, so I just kind of want to reel that in a little bit because I think it's a little overwhelming. Okay, but I wanted to give you a little bit of calculus here So our total impulse will then be from this last equation. If we took the integral, okay, we'll get some equation like so. Okay, so this is going to be the total impulse over some time interval, okay? Now we can rewrite this since we can recall, if you have seen this before, if not, that's okay. But this is a functional average, so we can take an average of this function f of x, and that's what we do here with our force. So we take our force average and we define it as so, okay? And if I plug this in, or if I try to relate this to this equation here, I will then obtain this smaller equation. Okay, so my J, or my impulse, okay, I should probably write that this is impulse, is now related to some F average over some time dt, or delta t, okay? So that way we don't have to go through all of this crazy math if we hopefully don't have to. That didn't make sense. Hold on. If it's not necessary, we don't really want to have to go through all of this calculus every time, right? So with that, we can calculate our impulse as follows. We can calculate it in a different way. So if we have some force, of course, F equals ma, right, from Newton's second law, we can go ahead and take that and plug it into our impulse equation here, okay, rewrite it as ma, okay, and then of course when we're taking the integral of an acceleration, we're going to get some velocity back. So this is what we'll end up with, okay, and if we have a constant force, so our F average is just some F, right, so we just have some force, we can then simplify this to plugging these values in again, and we get this is our impulse. So our impulse, as you can see, is very similar to our momentum, right? Because our momentum, remember, is equal to mv. Okay, this is momentum. Oops. So if our momentum equals P equals mv, that means if we take the change in that, which is our impulse, then we'll get m delta v, which makes sense, right? Okay, so let's go ahead and do an example. So this is example 9.2, and we're going to be looking at benefits of impulse. Okay, so it states a car traveling at 27 meters per second collides with a building. Okay, the collision with the building causes the car to come to a stop in approximately 1 second. Let me go ahead and do that. The driver, who weighs 690 newtons, is protected by a combination of a variable tension seatbelt and an airbag. In effect, the driver collides with the seatbelt and the airbag, not with the building, right? Because there's that protection there. So the airbag and seatbelt slow his velocity such that he comes to a stop in 2.5 seconds. Okay, so the car might stop at 1 second, but he will continue to move forward until that seatbelt and airbag take into effect. Okay? So, the first question is, what average force does the driver experience during the collision? So we want to know F average. Okay. Okay. So F average is going to be related to MA, right? And we do have this formula here. So let's see. F average is going to be the weight of the person over some amount of time that it takes him to stop, I believe. Okay? So what we'll do is we'll go ahead and take that F average, okay, as M A bar, okay, and we're going to also set that equal to, or not set it equal to, I'm sorry, we are going to relate that to our impulse equations. Okay, so our impulse J is equal to F average delta T. Okay, we have J is equal to F average delta T. Okay, we also have from our last equation here is that the impulse J is equal to M delta V, equals to M delta V. Okay, so we can find that average force with this equation here. Okay, so let's go ahead and do that. I guess we didn't need this part. Okay, that's okay. Sometimes it's better to write down all your equations and then figure out what you need. Okay, so let's go ahead and say F average is equal to M delta V over delta T. Okay, so now we need to figure out what is his velocity is and what is the change in time. Okay, so let's see. He has, let's see, the velocity of the vehicle is 27 meters per second. Okay, the vehicle comes into a stop for 1 second, but he stops, let's see, force driver experience during the collision. He comes to a stop at 2.5 seconds. So I would say his delta T is 2.5 seconds. Okay, his mass is going to be related to this weight here. So remember that F is equal to mg. Okay. So then his mass would equal F, this force, over g, or the gravitational constant, and we can go ahead and calculate that real quick. So that's going to be 860 over 9.8 meters per second squared. So then his mass will be what? 9.8. His mass will be 8.78 kilograms. Okay, and then we'll have the velocity 27 meters per second. Okay, so our average force then, go ahead and calculate that, is mass times 27 divided by 2.5, and we get 948 newtons. So this is the average force that the driver experiences during this collision. Okay. So that is in part A. Now part B states without the seatbelt and the airbag, his collision time would be approximately 0.2 seconds. Okay, it asks what force would he experience in this case, and so we'd have the exact same setup. So F average would equal 8.78 kilograms times 27, but our time is different. It is only 0.2 seconds. So let's see. We would get a much higher force. Let me continue this in the next video. Sorry about that.